I was just trying to figure out if there's a faster way to count. That's a lot of counting. Okay, we are on the last round here. These are my marks. We have been around 10 times, and here we are. 8 plus 1 is going to be a 9, and 1 plus 9 is going to be 10. Drop the 10 category, we're back to 0 where we started. Okay, welcome back. It's early. First cup of coffee. Steam arising. And I'm kind of looking for the videos that I'm about ready to post online today. And I thought some of this is all going to be review, but it's going to mainly focus on the Every 9 Ikosagon, which I want to show you where I first drew that out. The Every 9 spiral. I did it on my window. I know. But aren't you glad I'm not using that to try to teach? What a mess. Anyway, so I've tried to make drawings that are much more clear. But I wanted to do a review on this 7th thing, just in case I haven't shown the comparison. Oh, where is it? Here it is. I know I've already shared this, and that I got this from the book Philomath, the geometric unification of science and number, and I got it. Oh, it's in here somewhere. Great book, by the way. Right here. There. That is that. And but I'm not sure if I explained that I added to it. The part I got from Philomath is all these outside, where if you add from here to here, it adds up to a 6. Where if you add from here to here, all these numbers add up to a 9. So you actually have a continuous 3, 6, 9, 3, 6, 9. It looks like they changed direction. See, 3, 6, 9 is going on this ring, and then on the other ring, it's 3, 6, 9 is going the other way. Fascinating. But what I did is I took it a step further because of after doing this, okay, and this hypothesis that God is one and rests on the 7th, and the fact that 1, 4, 2, 8, 5, 7 could be used via contraction and expansion to grow the seed of life. I shared that in one of the videos. I think I also shared that I noticed there's a doubling pattern within it. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, etc. And some coffee. I thought that's really interesting, especially when I took the numbers between the 3s and the 6s, like 5 and 1 and 4 is 10, so 1 plus 0 is 1. You pull it off. 2 plus 8 plus 1 is 11, and 1 plus 1 is 2. 1 plus 1 plus 2 is 4. Pull it off. 5 plus 4 is 9, plus 8 is 17, and the 7 and the 1 make the 8. So when I added the numbers between and pulled them off, I got a 1, 4, 2, 8, 5, 7, 1. and in the outer ring here, I got a doubling pattern again. Just like this doubling pattern is the toroidal. 1, 2, 4. 1 times 2 is 2. This doubling pattern is on the circular. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, which is a 7. 16 times 2 is 32, which is a 5, etc. They're almost the same, but it's just like they're seen from a different perspective. Again, it seems to be no matter how I slice this, it's the numbers are doing math. I wanted to make sure that I've shared this because it's just I'm going to pursue this, and if this really is the vibrational proportions used to basically when God spoke the world into existence, and if the mythology in Genesis that God is one and rested on the seventh day is actually God is one and rests on the seventh, I mean, I would not be surprised. Okay, let's get into the prime numbers. Let's see. This doesn't show up very well, I know, but I thought it was really interesting that when I got this printout from the library and of all the Fibonacci numbers, they were very kind enough to label which ones are primes. See that? And I thought, then I noticed, wait a minute, that's a prime, and it's on a 29. Number 29, the 29th Fibonacci number is a prime. Wait a minute, that's a prime number, but it's falls on number 23, which is a prime. Oh boy, that's a prime number, and it falls on 17. This is a prime number, and it's on 47. Yes, every single Fibonacci prime number. This I know everybody out there trying to solve the Riemann hypothesis is going, holy shit, because there's $1 million prize for whoever can prove or disprove the Riemann zeta function. Unfortunately, I'm not. I don't know enough math to put it into a formula, but we are looking at another pattern here. We're looking at a pattern that just came off a printout from the library. The only number that doesn't follow this pattern is the 3. Prime number 3 is actually the 4th Fibonacci number. That's the only number that doesn't, even 2 falls on a 3, which is a prime. So that is the only one. Attention, anytime something is out of place, that may be a key as to something else. Every time I found something here that's out of place, oh, wait a minute, why isn't this geometric shape doing math? I always look a little closer. Man, I'm not hurt. The pen, one of my pens was leaking. But I thought this was fascinating. It's even, it follows through. And let's see, I go to the next page. This big long prime here, see that big long prime? Falls on 83, which is a prime. Isn't that something? I know. It's so cool. And let's go to some really big numbers. That is a Fibonacci number, and it's number 131, which is a prime number. This is a Fibonacci number right here, and it's number 137. OMG. Okay, so I wanted, since we're talking about primes, I wanted to show this again because that's just amazing. Okay. And let's see. No, that's not what we're gonna do. This is a t-shirt idea. This is what we're gonna do. The every night icosagon. Okay. Yeah. Because this, we're not gonna do this right now either. We're gonna put it right there. Okay. Are we getting a good picture? That's not bad. Okay. That's not bad. Cool. So yeah, when I found that every 9 in the clockwise direction is adding to itself, and then I realized, wait a minute, 9 does not go into 60, and this is the last digit of the first 60 Fibonacci numbers that repeat over and over to infinity. So like the 61st Fibonacci number is going to be a 0. The 62nd Fibonacci number is going to be a 1. This cycle repeats to infinity. And this is, we don't have to use digital reduction on this wheel. These are just the actual numbers. And the reason we dropped the 10 category is if you were like, if you're adding up these Fibonacci numbers, you know, you added 2584 to 4181, you know, you're going to get a 5 here where the 4 and the 1 come down and make a 5, but then the 10 column is going to, you know, go into the next column just when you're adding up numbers. That's all this is. That's why we dropped the 10s, because like let's see, 8 and 3 is going to be 11. Well, we put down the 1, but then the 10 column is going to go into the next column of numbers. You see what I'm saying? And so we just, that's what these are. These are just the last digits of these. I mean, these are right down the line. It's going to be the last digit right down the line. I'm going to read them off the list here. You can read them off the list here. 1, 1, 2, 3, 5, 8. I'm just going to read the last digit. 3, 1, 4, 5, 9. You see what I'm saying? Yeah. It's just like, this is the actual list of the Fibonacci numbers, and these are the actual last digits of this list. Yeah, that's it. Finally, I think I found a way to explain that clearly, I hope. Yeah, so like if I was just highlighting the last digits, it'd be that, all the way up to the 60th digit, which is on this page. Here's digit number 60. Okay, and the last digit is going to be what? 0. So you go all the way around, and your 60th digit, that would be 0. Your 61st digit now is going to be 1, and there it is. Your 62nd digit is going to be 1, and there it is. Your 63rd digit is going to be 2, and there it is. See what I'm saying? Your 64th digit is going to be 3, and there it is. And then this cycle will repeat every 60. So if we went all the way up here to the 120th digit, okay, where it starts over again, 0, 1, 1, 2, 3, 5, 8, 3, 0, 1, 1, 2, 3, 5, 8, 3. See, it just keeps repeating to infinity. If we go up to the 180th digit, which is right here, we've got 0, 1, 1, 2, 3, 5, 8, 3, 1. 0, 1, 1, 2, 3, 5, 8, 3, 1. You see what I'm saying? Okay, cool. We're on the same page. Good talk. So this every 9 does not go into 60. So it goes beyond 60 for 3 revolutions, and every time, and it's adding to itself. Let's do that. This is so much fun. I know, I don't have anything set up. I don't have the links. I don't have the links to Jane's book set up. I don't have the links to... Honestly, I'm such an idiot. I don't even know how to do it yet. And I don't know how to set up... I want to make t-shirts, and we're going to have a slogan like, the angels got my back. And I want to put this on the back of a hoodie. And on the front, I'll have like a you know, I'll shrink this down into an emblem like Angel 369 and on caps and stuff, and because let's face it, I'm not going to solve the Riemann hypothesis. I can't function at that level right now. But somebody else might use these numbers to do that. So, but I can sell a T-shirt. But I got a good friend. His name's Mike, and he's going to set me up to where we can get these T-shirts, because I want these numbers in front of us all the time. And then I'm not ready to write the book yet, because the more I'm working on this, the more I'm getting. You see, I didn't get the prime numbers until last month when I started working on this to share it with you, and then all of a sudden I'm receiving all this information about how the Fibonacci sequence is actually separating through this every 9 icosagon the even numbers from the odd numbers. You see that? Look, every number we land on here. Sorry, my voice is so. I'm not awake yet. I can tell I got. Wake up, Jim. If we count it out, let's do that. Let's make sure you can see it up there. Yeah, okay. Start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4. 0 plus 4 is going to be 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there it is, 4. 4 plus 4 is going to be 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. And so on and so forth. The present plus the past makes the future number. It's the same way the Fibonacci sequence, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. It's the same manner in which the basic wheel itself is assembling itself. Any two of which are a seed. If you just started with 3 and 5 and did 3 and 5 equals 8 and did this all the way around, you would end up with exactly this wheel. These are all the seeds. 4 and 3 is a seed. 37, which is a Fibonacci, which is a prime number, is a seed. And see, when I noticed that, wait a minute, this every 9 icosagon just separated all the even integers from the odd integers as it went around adding to itself for 3 revolutions and then landed back right where it started, so it starts over again. This is a constantly repeating pattern. And on using the graph paper, I have done the every 9 icosagon. It's in here. Every 9 icosagon, and using these numbers that it lands on in the order that it lands on them. If you start at X, move the first number and turn right, move the second number and turn right, you will do all this and you'll land right back where you started. This is a constantly repeating pattern. Okay. Well then, I pulled all these even integers off to the center here and drew these lines between them and realized it's doing the same thing. Yeah. 8 plus 0 is 8. Yeah, 8 plus 0 is 8. 0 plus 8 is 8. 8 plus 8 is 16. Yeah. And you keep the 6. Drop the 10. 8 plus 6 is 14. Keep the 4, drop the 10, goes into the next column. 6 plus 4 is 10. Keep the 0, drop the 10. 4 plus 0 is 4, and 0 plus 4 is 4. 4 plus 4 is going to be 8, and so on and so forth. Pretty cool. So whenever you have a 20-pointed star, it's a 20 is icosa, and when it's a point, it's called a gram. If this had sides, it would be called a gon. So this is a icosa gram, and I call it the every 9 icosagram. Every 9 for 3 orbits in base 10 in the clockwise direction. Now, when I realized, wait a minute, this is separating even integers from odd integers, I made this drawing. I put love in the middle. We need more love in the world. And so, I just highlighted the evens and the odds, so they'll just jump out. And these lines drawn around the periphery, and the 20-pointed star in the middle is both the icosagon and the icosagram in action. No matter which way you slice these odd numbers, it's creating either primes or semi-primes. 19 is a prime. Down here 11, it's a prime number. 35 is a semi-prime, etc. Even if you go back and forth, if you go from, I thought that was fascinating. So now I got this. This is known, and again, Robert Grant and Talal, they shared this in this book about the Maltese cross. I'm not going to get that. And how that if you do a 24 wheel, this is 1 through 24, and then this is 25, 26, 27, you go around another 24 to 48, and then you jump up here to 49, 50, 51, do another 24 to 72, and jump up here 73, etc. Prime numbers and semi-primes tend to line themselves up on the leading edges of this Maltese cross. Everything circled here is a prime number. 5, 7, 31, 29, 53, 101, 103. Pretty cool. Okay, this is known. So I think I've already shared, I took it to another level, and I decided to do a 60 wheel. Okay? And starts right here, 0, okay, like 1. Here, it starts with a 1. 1, 2, 3, 4, 5, 6. Just do 1 through 60, all the way around here. When you get to 60, jump up here to 61, 62, 63, 64, 65, go all the way till you get to 120. And now this is 121, 122, 123, 124, etc. And lo and behold, sure enough, the primes line themselves up on these highlighted rays here. These are all primes, folks. And the ones in the middle, yeah, it's amazing. It's very symmetrical. You've got 2 rays, and then 1 ray, and then 2 rays, and 2 rays, and then 1 ray, and then 2 rays, and 1 ray, and then 2 rays, and 2 rays, and then 1 ray. So these, you got 2 rays on either side, and you got 2 rays on top and bottom. And between that, you got 1 ray, 1 ray, 1 ray, and 1 ray. And wow. Okay. Again, we're looking at patterns and of prime number distribution. The Riemann hypothesis should be solvable. I mean, we're picking up a lot of patterns here. And I wish you guys luck, girls. I could use $1 million. Who couldn't? Thank you, Clay Mathematical Institute, for putting up the prize. And this is the first time I did it. So I started to notice something, though, when I looked at this one. Okay? When I looked at this, okay, I thought, oh, wait a minute. It's upside down. When I looked at this, remember how, oh, we need inspiration. Here, let's put that in the middle. Okay. So, remember how every 3 this direction, if you start only where the funny thing is about the every 3 in the counterclockwise, it only works if you start at one of these even integers. And then, of course, the every 5 in the clockwise direction add together. And then we've already covered the every 7 in the counterclockwise for 7 revolutions add together. And that's when my mind really started opening up about the prime numbers and their distribution within the Fibonacci sequence, because I thought, wait a minute, every 3, every 5, every 7, and ironically, they seem to be separated by the every 9. Okay, which is not a prime number, but the every 9 seems to be doing the separation of these numbers. Okay, so I thought, well, what about the rest of the prime numbers? What about every 11? What about every 13? What about every 17? What about every 19? What about every 23? And guess what? It's real. It is actually real. So I made this. And I'm going to play a little clip here because I took the time. I'm going to cut this right here because I took the time to actually count every 11 for every 11. Yeah, I did it with my calculator, dude. You can do it with your calculator, but I counted every 11. Watch this. This is just bizarre. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 9. So what is 0 plus 9 going to be? It's going to be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there it is. Okay. What's a 9 and 9 going to be? It's going to be 18. So we're going to look for an 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What's a 9 and 8? It's going to be 17. We're looking for a 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 7 and 8 is going to be 15, right? Yeah. So we're going to be looking for a 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I kid you not. And of course 11 does not go into 60, so it goes beyond. Matter of fact, none of the primes go into 60, which works out perfect, because then you count beyond it. Okay? So what were we on? 7 and 5 is going to be 12, so we're looking at a 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there it is. Oh, somebody really wants me. It works. So I counted every 11 for 11, and I'm gonna post a clip of that. Okay, we are on the last round here. We have these are my marks. We have been around 10 times, and here we are. 8 plus 1 is going to be a 9, and 1 plus 9 is going to be 10. Drop the 10 category. We're back to 0 where we started. And then I counted every 13 for every 13. And then that's just too much counting. So I got my calculator, and I did with a calculator, I did every 17 for 17 revolutions. And every 17 for 17 revolutions, by the time you get around 17 revolutions, you're going to come back and you're going to land right where you started. And you'll have landed on every single digit one time and one time only. And that is true for every single one of these. Let's keep counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, I'm going to mark this right here. I'm right there. Stay. And I'm not going to make you wade through all this, but I'll come back on just before I finish up, because what's really cool is I'll start adding all sorts of different colors, and this is going to turn into a piece of artwork. Yeah, later. I might do it in fast motion. Okay, it's getting close. 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Remember, we want to come back and land on this 0. 1, 2, and now we have just passed 0, so we give this one more mark. We're at 15 revolutions, and we want to go for 17 revolutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Although I have not counted beyond 17 for 17 revolutions, because I just got burned out. If you want to count 19 for 19 revolutions, cool. If you want to count 29 for 29, I have gone all the way up to 29 for 29 revolutions using my calculator, okay? And but a lot of these primes, you realize, I know they're going to work, because let's just take every 7 for 7 revolutions as an example. Every 7 for 7 revolutions adds together. The past plus the present equals the future number. Well, if every 7 for 7 revolutions in the counterclockwise works, and this is a 60 wheel, then every 53 for 53 revolutions is exactly the same thing in the counterclockwise, or in the clockwise. 7 is counterclockwise. Okay, so this way. So, because if I come around here and come around 53, I'm going to end up 1, 2, 3, 4, 5, 6, 7. I'm going to end up on that 3. because the 50, that is the 53rd number. Yeah, and when I go around again, it's going to be down here, 1, 2, 3, 4, 5, 6, 7. It's going to be right there. And when I go again, 53, it's going to end up down here on this 6. Okay, so the 53 and the 7 kind of go together. Okay, the every 11 in the counterclockwise, its counterpart is going to be every 49 in the clockwise. Do you see what I'm saying? And that's going to work. If that works, that's going to work. So all I had to really do is count every 20, and so I went up to every 29 for 29 revolutions with my calculator. I've gone up to every 17 for 17 revolutions, physically counting. And what's really cool is you've always heard about angel numbers. Like you see an 1111, it's like, oh, that's an angel number. You know what? It really is an angel number. These are the angels, and they're using these somehow these prime numbers are performing a function within the Fibonacci sequence. I mean, this just defies chance in so many ways. Yeah. So, what else was I going to share about prime numbers? This might have been it. I think this is it. Probably not. I'll probably have to come back on. And is there anything here else here I was going to share? So, my shortest video. Wow. No, I think this is all I was going to share about prime numbers. This is all I know so far. That's as far as I got. All right. If you like, give me a thumbs up. And if you want to subscribe, go for it. And I will eventually. I want I want this on the back of a hoodie. With a slogan over the top of it, "The angels got my back. How about yours?" With a big question mark, okay? Yeah. And on the front of it, I want something to do with something like this. I want a logo like this, because this is, of course, the 369. Once you understand the shapes and the numbers that these points fall on, once you understand this unicursal hexagram is on the 3, the 6, the 9, the 3, the 6, and the 9, you don't have to know the numbers, okay? The squirrel just ran across the top of my trailer. Matter of fact, once you realize that the perfect seventh follows, I'm going to show you an example. This is a better example. Once you understand the perfect seventh parallels, it's upside down, the 369, you don't have to know those numbers, because I know this is a seventh. So I know that's a 1, that's a 4, that's a 2, that's an 8, that's a 5, that's a 7, and that's a 1, because of the pattern. They parallel the 369. That's a 1, that's a 4, that's a 2, that's an 8, that's a 5, that's a 7, that's a 1. So I kind of want to have both wheels on my back, so or on my clothing. So I'll shrink this down probably and make it into a logo, and put ET there saying, "Hey, chill out, dudes." Make love, not war. And because I want to have the 24 wheel and the 60 wheel on my clothing. Okay, so yeah. All right, that's it. I'll probably play a song now, because that's what I do. Peace out, and may peace be with you, and may the angels have your back. May God be with us all. 17! Yeah, we're there. 17. I don't know if you can see that. Can you see that? Wait a minute. Oh, yeah, 17 revolutions. And we have landed on every single letter or number once. Look at this. Once only. 17 revolutions. So we have just proved out all the way up through 17 by 17. Next, 19 by 19 in the opposite direction. I think this is actually going to prove itself out. The angel numbers so far are doing exactly what the it seems to be. Okay, later. Just lined up to the bullseye. It's almost impossible. My face is a foot from the ground. My face is a foot from the ground. This could be bad.